Hello. I'm gonna wait for a few more people to join. Dum de dum. Happy Friday, everyone. Waiting for about 20 people to join up, and then I will get started. Hello, sir. All right, we've got 20. Here we go. All right, hello, class. Going to start off with a couple of announcements. First of all, if you are interested in taking the AP Physics 1 exam, on my Canvas front page, I have all those buttons for our Zoom room and all that stuff. Below the buttons, I have placed the join codes for the AP Physics 1 exam. So you need to have those codes if you want to sign up for the exam, so they're there. And you can, I believe also it allows you to access the resources that College Board has for AP Physics 1. Okay? That's thing number one. Thing number two is in the next probably 2 weeks, we are going to have a midterm. The midterm is going to cover the stuff from the first triad. So there's 1 week left in the first triad. And 1 week left in the first triad. So the following week, you will have a midterm. And I'm going to give you the whole week. You will have 3 hours to complete the midterm once you've started. So I'm doing it that way because I know some of you have unstable internet, and I don't think it's going to take you 3 hours, but I just want to make sure you have enough time to get to a new location or for your internet to be restored. But you'll have 3 hours. That'll be worth 100 points, so it'll be worth, basically, it'll be equal to the amount of points we've had so far, a little bit less than the amount of points we've had so far. You're going to get one attempt. I'm going to keep the questions super straightforward, so my goal is not to try to trick you. My goal is to be very direct and just make sure that you understand the content. Okay. The third thing I wanted to talk about is that in the next 5 days or so, I might have to move my office hours around, and I might be a little bit less responsive via email. And that is because my parents are visiting. They're probably they are driving an RV down from Washington State, and they're at about the Grapevine right now. So they're going to arrive this afternoon, and so I'll be spending some time with them, and I might not be checking my email as often. I might move things around to accommodate the stuff that I'm doing with them. But I will still meet my obligations to have your office hours. Okay? All right. So I'm going to go ahead and get started. AP Physics 1. I am really tired today. AP Physics 1, October 2nd, period 6. All right, so let's talk about this kinematics equation right here. Delta x equals v naught t plus 1/2 a t squared. So we've used this equation a lot so far. And in all the problems that we've done, the acceleration has been a given. So I have said the acceleration is this. But we haven't really talked about what makes the acceleration that, as opposed to some other value. So that's what we're going to try to answer now. What makes the acceleration have a certain value? Okay? What gives the acceleration a certain value? And so to answer that question, oh my gosh, here it comes again. It's weird. I guess I woke up at 5:30 and I went for a run this morning, so maybe that's why I'm tired. Okay, so to understand what makes the acceleration have a certain value, we have to discuss something called a force. Okay, so we're moving on from kinematics and we're going into our next topic, which is forces, which is basically going to tell us why does the acceleration have a certain value. Okay, so a force is a push or a pull with a certain strength and a certain direction. Okay, so the direction of the force could be to the right or to the left. It could be up or down. It could be diagonal. The strength is how strong is that push or pull. Okay. In physics, we very often encounter things that have strengths and directions. Okay. So this actually has a special name. Any mathematical object that has a strength and a direction is called a vector. So force is an example of a vector. Velocity is an example of a vector. So you might have learned about vectors in your math class. If not, that's okay. But vectors are all over the place in physics. So throughout this year, I'm going to teach you how to do calculations with vectors. Yeah, so by the end of this year, you'll be an expert in that sort of thing. I will denote a force by F, okay? And square brackets around a quantity means units of. So the units of force are called newtons. N, named after Isaac Newton, who was commonly thought to be the first sort of theoretical physicist. He kind of, before Newton, they were figuring out kinematics kind of before Newton, but Newton came up with the idea of the force, okay? And he really sort of put it all together into a consistent framework. So he gets the unit of force. All right. If you have lots of forces, okay, so for example, if you have, let's say you had a 5 Newton force going to the right, and then you have a 7 Newton force going to the right, and you have a 10 Newton force going to the left, and you have a 30 Newton force to the left. It is possible to combine those into a resultant force, okay? We all have lots of forces acting on us, lots of pushes and pulls acting on us all the time. For example, we're being pushed on by the atmosphere. The air molecules are bouncing into our forehead, into our face, and pushing on us. Gravity is pulling us down. If you're sitting on a chair, the chair is pushing against you. So we have all these pushes and pulls happening all around us all the time. Okay? And the total result of that is called the net force. Okay? The net force. And it's the combined result of all the forces that are acting on something. Okay? And to calculate the net force, you just add together everything. So however many forces there are, you add them together. Okay? So I put plus dot 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 to indicate that there could be more than 2. So in this example, the net force, and we use the same sort of conventions that we had before, where if something is going to the right, we'll just call it positive. If it's going to the left, we'll call it negative. Okay. And so we've got a 5 Newton force to the right and a 7 Newton force to the right. So that's plus 5 and plus 7 contribution to the net force. And then we have 10 newtons to the left and 30 newtons to the left. So that's going to be minus 10 and minus 30. Okay? So what is that? That's 12 minus 40. So that's a net force of negative 28 newtons, which we could also say is a net force of 28 newtons to the left. Okay? So that's how you get the net force. It's possible to have a net force of 0 while having forces acting upon us. Who can give me an example? Type it into the live chat if you know. What would be a situation where you have a net force that is 0, but you have forces acting on you? You have non-zero forces acting on you. How can you have non-zero forces acting on you but still have a 0 net force? Okay? If you think you know the answer, go ahead and type it into the live chat. While I wait for an answer, I want to talk about what is 1 Newton of force. Okay? What is 1 Newton of force equivalent to? What is a strength of 1 Newton? Turns out that 1 Newton, if I grab the collar of my shirt and I pull lightly, sort of just tug on the collar of my shirt, that's about 1 Newton of force. If I just pull on my earlobe just with a small tug, that's 1 Newton of force. So 1 Newton is basically a small tug. So a human who's pushing on something as hard as they can is going to be able to exert a couple hundred newtons of force. Okay, so I think maybe my question was a little bit confusing to you. What if you had a force that's going to the right with 100 newtons, and then you have another force that's going to the left with 100 newtons? In this case, your net force would be plus 100 minus 100 equals 0. Okay, so if you have equal and opposite forces acting on you, then that means that your net force is going to be 0. All right, so that if the forces cancel each other out, you can have 0 net force, even though there are lots of forces acting on us. So right now, for example, I have no net force acting on me. Okay, even though I have individual forces, I have gravity pulling me down, but I also have my chair holding me up. So I have these two forces that are kind of counterbalancing each other. Gravity pulling me down, the chair holding me up. Okay? So what we're going to do is we are going to now talk about Newton's laws of motion. Which you've probably heard of before, but we're going to talk about them at a deeper level than you have before, I hope, at least. So Isaac Newton came up with these in the 1700s, and it has basically started the field of physics, okay, by him stating these laws of motion. So the first law of motion says, objects in motion stay in motion objects at rest stay at rest unless acted upon by a net force. Okay? So this is sometimes called the law of inertia. Okay? Inertia is the tendency of matter to just want to stay put if it's staying put, or to keep moving if it's already moving. Okay? So you could think about Newton's first law of motion as basically a statement of cause and effect. Okay? The effect is a change in motion. Okay? All right, the effect, because a change in motion would be if you're at rest and you start to move. Okay, if you're in motion and you come to rest, that's a change in motion. So the effect is a change in motion, and the cause of that is a net force. Okay, so if I wanted to state the first law of motion in a more mathematical way, I would say that the acceleration of the object is equal to 0 if the net force is equal to 0. So the motion doesn't change. So acceleration is the rate of change of velocity. So if your acceleration is not 0, that means your motion is changing. So the acceleration being 0 means that your motion is staying consistent, and that happens when the net force is equal to 0. Okay? I like to think about what would the universe be like? What would the universe be like if Newton's first law was not true? Okay? What's the converse of Newton's first law? It would be a universe where objects in motion do not stay in motion. Objects at rest do not stay at rest, even when acted upon by no net force. So it would kind of be like, something flies through the air and it just randomly stops. Or something that randomly is stopped will just start moving without any reason for it. So it would be a very chaotic universe where things are just starting and stopping and changing direction without any rhyme or reason to it, okay? So Newton's first law is saying that if that motion is going to change, there has to be a reason for it, and that reason is a net force, okay? The second law of motion expands upon the first law of motion. So the second law is a more detailed version of the first law, and it's an equation, and it's undoubtedly the most important equation in classical physics. Okay, there are more important equations if you learn like super advanced physics, but if you're going to be a mechanical engineer, you're going to be, for example, this is the single most important equation in mechanical engineering for sure. It's Newton's second law of motion. It says that the net force equals mass times acceleration. Okay? So M stands for mass. Let me just remind you what mass is in case you forgot from your previous classes. Oh my gosh. Mass is a measure of the amount of matter. Okay. The units of mass that we will use in this class are kilograms. Okay. So Newton's second law is a more precise statement of cause and effect. Okay, it says the net force is the cause, and acceleration is the effect. Okay, and so it tells you what the size of the effect will be for a given cause. All right. So in order to make something accelerate, you exert a net force on it. But if you exerted the same net force on two different objects, so if you have a constant net force, then M times A have to multiply to a constant, right? If the left-hand side is constant, then the right-hand side has to be constant. So what happens as the mass goes up? Well, if the mass increases, then the acceleration decreases. All right? So basically what the second law is saying is that it's harder to move around massive things than it is to move around lighter things. You need a bigger force if you want to move around something that's very massive. Okay? So it's a precise mathematical statement of something that you all of you know about already. Okay? You all know that if you want to move something that's very massive, you have to push hard, right? That's all Newton's second law is saying. Okay, it's a precise mathematical statement of that. Let's do an example. Okay. Here it comes again. Woo! All right. So let's do an example where you have an object experiences a 300 Newton force to the right and a 70 Newton force to the left. If the object starts at rest, okay, and has mass 15 kilograms, how fast is it going after 7 seconds. So there's an example for you. An object experiences a 300 Newton force to the right and a 70 Newton force to the left. I should state, in order for this to make sense, I have to say that these are the only forces. Okay? Those are the only forces. Why is that? Well, because Newton's second law has to do with the net force. All right? So what would be the problem with saying something like this? What if I said one of the forces on a 2 kilogram object is 10 newtons? Okay? So then that would mean that 10 equals 2a, which says that the acceleration is 5 meters per second squared. What's wrong with that statement, saying that one of the forces on an object is 10 newtons? If it has a mass of 2 kilograms, it must have an acceleration of 5 meters per second squared. Type it into the live chat if you know the answer to that. Okay, so we've got this 300 Newton force going to the right, and we've got a 70 Newton force going to the left. I'm representing that as a shorter arrow to indicate that it is a weaker force. And so that means that the net force is 300 minus 70. Okay? So that means that the net force is 230 newtons. Not quite. I see someone answered my question. So the thing is, by saying one of the forces is 10 newtons, that doesn't mean that there aren't any other forces. Okay? If there are other forces besides a 10 Newton force, then that's going to change the net force. Okay? So in order to calculate the acceleration, we have to know all of the forces acting on the object. If there are any left out, then those left out forces are going to change the net force, which in turn changes the acceleration. Okay? So now I go to Newton's second law. Net force equals ma. I know that the net force is 230. I know that the mass is 15. So I divide both sides by 15. 230 over 15 is about 15. 15.3 meters per second squared. So notice, we have now answered my question from the beginning of the lesson. What makes the acceleration have a certain value? Okay, the acceleration has a certain value because of the mass of the object and the net force it experiences. Okay. Then, once we have this acceleration, I can then plug it into a kinematics equation. So we know that it starts at rest, so that means initial velocity is 0. We know that 7 seconds elapse, so that's time. And we want to know how fast is it going. So we want to know V final. So type it into the live chat if you know which kinematics equation is going to has those 4 pieces of information. I think I will wait. Waiting for someone to type into the live chat. Going once, going twice. No one is typing in. Oh, okay, awesome. Someone typed in. So the correct kinematics equation is the second one, which says V final equals V initial plus AT. V initial is 0. The acceleration is 15.3. The time elapsed is 7 seconds. So that means that the final velocity is 107 meters per second. Okay? So the net force and the mass determine the acceleration. The acceleration determines what the motion is going to look like. Okay? So we've taken this whole process back one step. Okay? We still got one more law of motion to cover. So let's talk about Newton's third law of motion. The third law of motion is often called the law of action and reaction. Okay? And what it says is that for every action, there is an equal and opposite reaction. Okay? So that's not very descriptive. So let's talk about it in terms of a mathematical equation. Okay? So what the third law says is that F(A) on B, so that's the force of Alice on Bob, minus the force of Alice on Bob is the force of Bob on Alice. Okay? So this is the mathematical statement of the third law. Okay? Equal in the sense that these two forces have the same size, opposite in the sense that they have the opposite direction. Okay? So what is a great example of Newton's third law is boxing. Okay? If you punch someone in the face with 200 newtons of force, so your fist exerts a 200 Newton force on someone's face, then that means that the face is going to exert a 200 Newton force back in the opposite direction on your fist. Okay? That force could be enough to break your hand. This is why people who punch things often break their hands. It's because of the reaction force. So the reaction force is the force of Bob on Alice. The action force is the force of Alice on Bob. Okay? So these are equal and opposite. If I walk forward, how do you walk? Well, you exert a backwards force on the ground, and then the ground exerts a forward force on you, which propels you forward. Okay? So let's do a little example. What if you're an astronaut in outer space? Okay, so there are no other forces present, and you punch another astronaut. Okay, so you punch that astronaut like so. There's your visor. There's his visor. Maybe his visor is cracked now because you punched him. And when you punched him, you exerted a 700 Newton force on the astronaut on the right. Okay? Maybe this person has a mass of 50 kilograms, and maybe you have a mass of 70 kilograms. So if you exerted a 700 Newton force on a 50 kilogram object, and that's the only force, you could calculate the acceleration of the right astronaut. You use net force equals ma. All right? the net force on the 50 kilogram astronaut is 700 newtons. Again, assuming that there are no other forces present. So 700 equals 50A. That means that the acceleration of the 50 kilogram astronaut is 14 meters per second squared. All right. Now, what's the story with the astronaut on the left? Because of Newton's third law, the astronaut on the left is going to have a force of 700 going back in the opposite direction. So if we were to do net force equals ma, assuming that this 700 Newton, force is the only force acting on the left astronaut, we would have that the net force on the left astronaut is negative 700, and that equals 70 times A, which means that the acceleration is negative 10 meters per second squared. One of the things you'll notice is that if two things are exerting a force on each other, the lighter one has the greater acceleration. Okay, 14 is a greater acceleration than 10. All right, you might have experienced this before. This is why it's good to be big if you're playing football, right? If I were to play football and I push on one of the linebackers is going to accelerate back like this, and I'm going to go flying across the room, okay? Because I don't have enough mass. My mass is small, so that, yeah. So I wouldn't be a very good football player. You just need mass, okay? Among other things, but mass is important for football. Okay. I want to talk about what would happen if Newton's third law was not true. What if for every action there was a reaction that was opposite but was not equal? What if the action and the reaction were unequal and opposite? Okay, let's think about that. Let's imagine a scenario where you punch yourself in the face. Punch yourself in the face. You exert a 100 Newton force on your face. But what if the reaction was less? So this is just hypothetical. This is not true. But what if the reaction was less? Maybe the reaction is only 70 newtons. Okay? In this case, because you are exerting a force on yourself, you're actually creating a net force on yourself. In this case, the net force on you would be 100 minus 70. 100 minus 70 equals 30 newtons. Okay? So if Newton's third law was not true, you could punch yourself in the face and exert a net force on yourself. If you exerted a net force on yourself, you would then accelerate. You would accelerate. The acceleration would not be equal to 0. So we wouldn't even need cars anymore. Okay? If you wanted to get to work or to school, you could fly. Okay? All you have to do is punch yourself in the face. Psh! Now I have a net force on myself, so I'm going to accelerate into the air. I can fly just by going punch myself, fly over the top of Laverne to Claremont High School. Okay, so that's obviously ridiculous. We can't do that. Okay, so one of the things that the third law of motion is getting at is the only way to accelerate yourself is to push off something else. Okay? The only way to accelerate is to push off something else. And so this is kind of sad because when you push off something else, it goes away, right? So it's kind of like if you want to go somewhere, you have to leave something else behind. All right? But then again, that kind of makes logical sense, right? If we could never leave something behind, then we would never be going anywhere because it would already be here. I don't think I've ever had that thought before. I'm going to ponder that more this afternoon. Okay, class. That is my lesson. So I will see you in the Zoom room to start the quiz. Bye now.